Welcome back. Let's look at assignment number 4A. Write a Python program to implement using insertion sort. Merge sort we have implemented, we have done it in 4C. So let's concentrate on 4A. The way it is done is we create a random list of 50 digits. Okay, this is the way to create it. And then we copy it into data empty data list, and then we pass this list to insertion sort. Like this is old methodology of implementing insertion sort, which is nearly brute force. So brute force in the sense very crude. We will see later merge sort, which is more sophisticated, which makes use of divide and conquer. This insertion sort actually basically bigger notation wise it's O(n) square, because two for loops are there here. So that is n, one n here, one n here, n into n square, order of n square for any given list. So that is execution time taken. Execution time taken. The other thing is time complexity, space complexity, space how much memory it requires. That analysis we are not doing here, but we are neither doing time analysis, but this insertion sort happens to be very slow. The way it is done is as you would have seen in the lower semesters, there will be two loops, outer loop and inner loop. Outer loop traverses if there are five numbers in the list, outer loop traverses from 1 2 3 4 5, and then inner loop will be one ahead of that. This loop will be one ahead of that. We do a comparison, and if the outer loop value is lesser than inner loop value, we swap it. Okay, so that is the basic idea. This is the way how insertion sort was defined earlier. Now there are of course other definitions of insertion sort, but let's stick to this old definition. So whenever outer loop value is lesser than inner loop value, we do swap. Let's run this program, so that things become clear. Okay, so here let's analyze the program. So it created a random list like this, okay, starting from 40 till 15, and it sorted it from 0 till 49. And in the main course, it did 2500 comparisons. Why? Because there are 50 numbers in outer loop, 50 in inner loop, so 2500 comparisons and 643 swaps. So of course, this can be improved in a bit improved version of insertion sort, but since insertion sort is a brute force, I didn't bother much to improve it or improvise it or whatever. So this program will also be there, but most important is you need to concentrate on this merge sort, which is a recommended sort because it is belonging to that divide and conquer family. In this divide and conquer, what we do is given list, we divide it into two halves, lower half and upper half, or left tree, sub right tree, whatever way you want to call it, and recursively we go on splitting the left tree, right tree, and then once we reach the value of individual leaves, like where leaf is one, we go on merging them. Okay, so that is how it is implemented here. Sorry, so that's how it is implemented here. So this is taken from very elegant implementation implemented in the algorithms in GitHub. I just took it. It is in with MIT license, free to distribute, free to use. Yeah, I can't write a better code than this for sure. So I just took this from the algorithms GitHub directory. Okay, this is the most elegant implementation of merge sort I have seen till date. So the way it is done is there is a nested function here, merge sort, and in merge sort there is a merge function. Okay, in merge sort function there is a merge function. The way it is done is def we skip here. We take first length. Okay, if it is less than or equal to 1, meaning we have reached the leaf node, last leaf node, we return the collection because the recursion has ended there. Else we divide it into two halves, okay, two halves, and then merge sort we call on the left tree, and we call merge sort on the right tree, and then they go on calling recursively till what point? Till the point when leaf node is equal to 1, okay, and when it is 1, okay, the way it is done is when it is 1, we go on calling merge, okay, we go on calling merge this function, and we go on merging them. How it is done? Okay, while left and right, okay, while left and right, result dot append, result is a scratchpad which is created internally here, okay, append. If it is left is smaller than the right, okay, we take left, else we take right, and pop one individual element from either left or right subtree, okay, and then okay we append it to result, okay. So result goes on increasing as this function is called repeatedly, till what point either left subtree has no value or right tree has no value. Once this condition is reached, we just do result plus left plus right, meaning whatever elements are left out in either left subtree or right subtree after this while loop are blindly appended to result list, okay. So this is to make sure we don't leave out any elements in the left tree or right tree, okay. Trace this program, you will get it. So yeah, let's run this program. I think we have to run it. See, unsorted is this, sorted is this, okay. So this program, as I mentioned again, it is with MIT license. You can try to emulate this program, very good program. So it is there in this GitHub directory. And this algorithm contains many other algorithms also, this you can take it as future learning pointer, meaning a place from where you can learn many future things, okay. Thank you.